This is part 1 of lecture 1.3 of Math 108, Logical Equivalence. In this video, we will define the concept of logical equivalence and use truth tables to determine if two propositional forms are logically equivalent. First, we define what we mean by logically equivalent. Two propositional forms are said to be logically equivalent exactly when their truth tables are the same. That is, P and Q are logically equivalent exactly when P and Q have the same truth value for any combination of truth values of the variables in the formulas P and Q. We use a triple horizontal bar to indicate equivalence. For example, consider the conditional sentence P implies Q and its converse, not Q implies not P. Recall that the statement P implies Q is false exactly when P is true and Q is false. It is true for all other cases. The statements not Q and not P have truth values which are the opposite of those of Q and of P, respectively. The statement not Q implies not P is false exactly when the statement not Q is true and the statement not P is false. That is, it is false exactly when P is true and Q is false. It is true for all other cases. We see that the columns for the statements P implies Q and not Q implies not P are identical. This means that for any combination of truth values of P and of Q, the statements P implies Q and not Q implies not P have the same truth value. Thus, the propositional forms P implies Q and not Q implies not P are logically equivalent. In other words, any conditional sentence is equivalent to its contrapositive. Now, let us consider the conditional sentence P implies Q and its converse Q implies P. The statement P implies Q is false exactly when P is true and Q is false, and is true for all other cases. Similarly, the statement Q implies P is false exactly when Q is true and P is false, and is true for all other cases. We see that the truth values of P implies Q and Q implies P differ in the second and third rows. That is, when P is true and Q is false, and when P is false and Q is true, the statements P implies Q and Q implies P have different truth values. Thus, the propositional forms P implies Q and Q implies P are not logically equivalent. In other words, a conditional sentence is not logically equivalent to its converse. To illustrate, let X be a real number and let P be the sentence X is greater than 1, and let Q be the sentence X squared is greater than 1. Since X is a variable, P and Q are predicates, not propositions. However, we can combine them using logical operators and determine whether the resulting statements are logically equivalent or not. We define logical equivalence of statements made up of predicates in the same way that we do for statements made up of propositions. The statement P implies Q is the sentence, if X is greater than 1, then X squared is greater than 1. Its contrapositive is the sentence, if X squared is not greater than 1, then X is not greater than 1. These two statements are logically equivalent. The statement Q implies P is the sentence, if X squared is greater than 1, then X is greater than 1. Its contrapositive is the sentence, if X is not greater than 1, then X squared is not greater than 1. These two statements are logically equivalent. Neither of the first two statements is equivalent to either of the last two statements. In the next example, we show that the three propositional forms, either not P or both P and not Q, either not P or not Q, and P implies not Q, are logically equivalent. We do this by comparing their truth tables. First, we fill in the columns for the statements not P and not Q. Recall that the truth values of not P and not Q are the opposite of the truth values of P and of Q, respectively. Next, we fill in the column for the statement P and not Q. Recall that P and not Q is true if and only if both P and not Q are true. It is false for all other cases. We now fill in the column for the formula either not P or both P and not Q. Recall that this is false exactly when both of the statements not P and not Q are false. It is true for all other cases. Next, we fill in the column for the formula either not P or not Q. Recall that the disjunction not P or not Q is false exactly when both of the statements not P and not Q are false. It is true for all other cases. Finally, we fill in the column for the formula P implies Q. Recall that the conditional sentence P implies not Q is false exactly when P is true and not Q is false. It is true for all other cases. We see that the columns of either not P or both P and not Q, either not P or not Q, and P implies Q are identical. This means that they all have the same truth value for every possible combination of truth values of P and Q. This shows that these three propositional forms are logically equivalent. Knowing which propositional forms are logically equivalent enables us to state any sentence in different ways without changing its meaning. To illustrate, let n be an integer and let P be the sentence, the integer n is odd. And let Q be the sentence, the integer n plus 1 is odd. The sentence either n is not odd or n is odd and n plus 1 is not odd has propositional form either not P or both P and not Q. This is logically equivalent to the sentence either n is not odd or n plus 1 is not odd, which has the propositional form either not P or not Q. It is also logically equivalent to the sentence if n is odd, then n plus 1 is not odd, which has the propositional form P implies not Q. This is the end of part 1 of lecture 1.3. Before you proceed to part 2, be sure to answer the exercises included at the end of these slides. Thank you for your attention.